Okay, this is a recap video to compare the SN1 and the SN2 mechanisms. So the thing that is one about SN1 is that in the first step, there is only one curly arrow and one reactant. This is a unimolecular mechanism. And so if I have my halogenoalkane here, the first step is that the halogen will break free from the rest of the molecule. And so I will end up, let me just write that smaller, because there we go. So in the first step, we draw a curly arrow leaving from the bond, going to the halogen, and the halogen will leave. And the halogen will leave with those electrons, so it will be negatively charged. And we will have created what we call a carbocation intermediate, a carbon species that has a positive charge. Now, it will always end up looking like this, sort of trigonal planar in shape, because carbon's fourth bond has just left, and that leaves the carbon behind with 3 bonds. In the second step, a distinct step in the reaction, the nucleophile, which is usually a hydroxide ion, in the IB anyways, will donate an electron pair to that positively charged carbon atom, and you'll end up forming an alcohol. I'm using R to represent just generic carbon chain, whatever the structure. So in the SN1 mechanism, we have one arrow at a time and only one reactant in the first step. In the SN2 mechanism, we have both reactants and both curly arrows in one step. That's why it's called 2. It's a bimolecular mechanism. So we get the arrow from the lone pair, or on the hydroxide, on the nucleophile, going towards a carbon atom, and we get the bond breaking. And so we get the same 2 arrows that we get in SN1, but they both happen at the same time. Now, that produces what we call a transition state. So again, we get this sort of trigonal planar looking carbon, but it would have the halogen and the hydroxide sort of both partially attached. So this transition state is showing the bonds breaking and forming. It has an overall minus charge because the hydroxide is sort of combining with the molecule, and so there's a net overall negative charge. And then afterwards, we end up with the alcohol, and we end up with the halogen ion, the negative ion. So overall, they produce the same stuff. The same overall reaction is taking place. We are converting a halogenoalkane into an alcohol, but the process of how that happens is distinct. And so you have to try to lock onto 1 meaning 1 arrow, 1 reactant, and 2 means 2 arrows, 2 reactants. Okay, now I need to skip way ahead in this packet to discuss the stereochemistry. Almost there. Almost there. Okay, here we go. Now, in HL, we also talk about chirality and this idea of optical isomers and enantiomers, these non-superimposable mirror images of each other. And so sometimes when we are doing a nucleophilic substitution reaction with a secondary halogenoalkane, we end up with a question where we might get asked about how the stereochemistry is affected, how the orientation of these molecules is affected. Because secondary halogenoalkanes, at least when we get up to like butane, so this is very common for them to use something like a 2-bromobutane or a 2-chlorobutane, because this is a chiral molecule. So this carbon here has 4 unique attachments. It has a CH3 group on the left. It has an ethyl group on the right. It has a hydrogen, and it has a bromine. And so as a result, it has 4 distinct attachments, and it is chiral. And so we know that that means it can exist as these mirror images of each other. So we could practice drawing those enantiomers here. So I would draw a carbon, and I have to try to draw the dash wedge structure. I draw my dotted line to represent the mirror plane, and I draw the dash and wedge structure again. Okay, and now I can fill in the attachments anywhere I want. I'm going to put the ethyl groups at the top just because I think they're the biggest to draw, and so I'll stick them there. They have a lot of space. I'll draw the methyl groups here, making sure that the carbon is clearly bonded to the carbon, and then I'll stick the bromine in the front, and I'll stick the hydrogen here. But you can put them anywhere you want, but so long as they are clearly reflected. So these are the two enantiomers, the two mirror images that exist for 2-bromobutane. There's two different molecules that exist, optical isomers of each other. Okay, now the point and how this relates to the nucleophilic substitution is that let's say we just start with one of these things. So I'm going to pick this one as my example. If I start with that one and I think about the SN2 mechanism, in the SN2 mechanism we have two arrows and we have two reactants at the same time. And so if the nucleophile is attacking this molecule, the SN2 mechanism always has what's called a backside attack, because the way it's always going to attack this carbon atom here, because this carbon atom is a little bit positively charged and this halogen atom is a little bit negatively charged. It's a polar bond towards the halogen. And so the hydroxide is never going to attack this molecule from the bromine side, because there's a negative charge, there's a little bit of repulsion there. So it's always going to attack from the backside away from the bromine. And so it's always going to come in from that orientation. The bromine is always going to leave from this orientation. And what that's going to do is it's actually going to invert the stereochemistry of this molecule, of this chiral molecule. And so in the end, if the carbon is here, the methyl group is going to get sort of pushed out in this direction. And the hydroxide that we bonded on is now going to be on this side. And the ethyl group is still up here. But you can see that this analogy is often used. It's kind of like an umbrella that gets blown out and gets inverted. And so when the hydroxide comes in here, from the backside, it's going to push all the other molecules away, all the other attachments on the carbon away to the other side. And so it inverts the stereochemistry. So that's one thing that it does. It inverts the stereochemistry. The other thing is that if we started with just this enantiomer here, we would also end with only one enantiomer being produced. Now that's again, if we start with one enantiomer and we do the SN2 mechanism, we will only produce one enantiomer. We'll produce the inverted version of the alcohol. Now with SN1, that is not the case. If we start with that exact same enantiomer from here, right, so we just have one version of the molecule here. When we do SN1, we form an intermediate that is completely flat. We form this carbocation intermediate, which is trigonoplanar. And because it's trigonoplanar, when the hydroxide actually comes into this mechanism, the hydroxide is equally likely to attack the carbon atom from one orientation versus the other. It can attack the carbon atom from both sides because the halogen has already left, which has changed it from this optically active chiral molecule into a flat trigonoplanar carbocation. And so because of how the mechanisms are different, we end up in a different situation about orientation. And so now that the hydroxide can attack from either direction, either orientation, if we started with just one enantiomer at the start, if something does the SN1 mechanism only, then we would expect to end up with a 50-50 mixture of the two alcohols when we're done. So we'd end up with half of our alcohols having that orientation, and we'd end up with half of the alcohols having this orientation. And that 50-50 mixture has a name. It's called a racemic mixture. And racemic mixtures are not optically active. Because you have both of the isomers, they both rotate light in opposite directions, and so the rotations all get canceled out, and it makes it so it's not optically active. Whereas when we just have one, it is optically active, and we'll get the full rotation of the plane polarized light by a particular angle in a particular direction. If you saw, so in this example, it says you've got the two enantiomers of butanol that can be formed, and they rotate light by plus or minus 40 degrees. So they could rotate the light 40 degrees this way, or they could rotate the light 40 degrees that way. So if no optical activity is detected in the products, you would know that you must have done the SN1 mechanism, and you must have that racemic mixture produced, where you have a 50-50 mixture of both enantiomers. If you have an angle of minus 40 detected, that would imply you'd only done an SN2 mechanism, because you have the full rotation that matches butanol's rotation. Therefore, you must have 100% of a particular isomer, a particular enantiomer. If you have an angle that's less than 40 but not 0, that implies that somewhat of the SN1 and the SN2 mechanisms must have taken place. So you're ending up with an uneven amount of the two enantiomers. So not 50-50, not 100 and 0, but something in between. Roughly, in this case, probably about a 75%, 25% isomer mix, since the angle is roughly halfway towards the other, something in that ballpark. You wouldn't be asked to state it so specifically. The point is, you're getting a mix, and you have some kind of uneven mix of the enantiomers. So we've got the two different mechanisms, and the two different mechanisms have a difference in orientation of attack, and therefore this topic of nucleophilic substitution, SN1, SN2 mechanisms, can be linked with the topic of chirality and optical isomerism if they want to make a really challenging HL organic chemistry question.